So Vicky's asked me to do a short introduction before we get into the program this morning. So first of all, I'd like to welcome everyone to the short course this morning and to the open house in general over the next couple of days. There was a question that I got posed to me at the beginning of this. Why do we hold these short courses, and where does your money go? And the answer to that is the open house is a self-contained thing. We raise all the money that we spend on the show. So this is one of the ways that we can put on a good show, make sure that registration is free, and keep getting the maximum amount of people into the show. So this is one of the tools we use to run the program each year. So our goal today is, as a group, is to learn about geophysics applications, but more so to learn how to integrate them with geology. And I think I always go to meetings and I hear things like, oh, that geophysics is voodoo and stuff like that. And I think that's sort of a passive-aggressive approach to it. Some people actually, because we don't understand what it means necessarily, we don't like the results of it potentially. So we need to learn how to integrate, as scientists, our models. Okay? And it might turn out that the model you had in your head doesn't fit the data. And so you might have that ability to let it go and come up with a better model. Times when money's tight, we need to make the best informed decisions, and integrating geoscience data is the best way to do that. So I think I'm just going to start this presentation now. So Vicky asked me to give this presentation just from the perspective of geologists, and I think we've got a fairly good mix in the room of geologists and geophysicists. Geologists...
Colin,
yeah,
emergency procedures.
Oh yeah, we have to do the emergency procedures. Thank you. She didn't tell me that.
You said you were doing it.
All right, so I don't even know where the nearest exit is from here, but certainly it'd be out these doors. I would think we would take the stairs down to the front of the room if there is an emergency. We have had fire alarms go off during this conference before. So we'd go out the front door, I think would be closest. I don't think there's anything that way. Bathrooms are just down the hall to the right. And anything else we need to know this morning?
The rally point's probably across the street at a double decker. So
I don't know if the bars are open yet. There is a provided lunch today. Okay, there's going to be a coffee break at, I think, both in the morning and the afternoon.
Yeah.
Last thing I was asked to do by Dustin out front is these badges are not your open house registration badges. Okay, so the registration booth is not set up yet. It should be sometime this afternoon. So once you get out of the short course, you should be able to go and pick up your registration package on this floor. Just keep going that way. You'll find it. Okay, so now I'll start. Okay, so I'm one of the geologists who tries to use geophysical information to enhance my interpretations, and so I thought I'd give a little bit about my experience over the last, longer than I'd like to say, what I've learned over that period of time about using this type of data in my modeling. Before we start though, I came across this article on CBC about a month ago about using cosmic rays to image the Great Pyramid of Giza, and I decided to click on it to see, and it was pretty uncompelling, but there were some great quotes in here, and I'm going to read these quotes for you here. So this is what the guys who found the void said. They said, what we are sure about is that this big void is there, that it is impressive, that it was not expected by, as far as I know, any kind of theory. We open the question to Egyptologists and archaeologists, what could it be? That's what we're doing here today. Okay, we're going to be talking about responses from rocks that might be anomalous and try to come to a conclusion about what those might represent. That's our job, and that's why we're here today. So to that end, this is what I hope to discuss this morning and generate some conversation with. So the first question I asked is, does the observed geology always explain the geophysical response? And so I played a game here. I added the word observed into this sentence. So if we take that word out, the answer is most certainly yes. But if I leave the word in, that might not be true. Okay? So then we'll talk a little bit about using various data sets. I've got a few case studies from my years of looking at aeromagnetic images in the Athabasca Basin area, and then we'll talk at the end a bit about integrating data sets. So before we start though, I grabbed this seismic section out of the X-Tech volume, and this is from MacArthur River area, back in the 2007 publication. And so what we see here is a profile of the crust in a seismic section. The Moho is down here at 35 kilometers, the Athabasca unconformity is right up here. And realistically, we've seen less than a kilometer of the top of that section in terms of what rocks are there. That's all we've seen. And 500 to 600 meters of that section are the Athabasca supergroup, which we consider to be geophysically transparent in some ways, at least in aeromagnetic data. So now really we're trying to make a geological model for, say, a geophysical program we've run on the upper 100 to 200 meters of the basement there, the subcrop. Now is that reasonable? Sometimes the geophysical features are more deep-seated than that. Are we going to be able to explain everything by that drilled amount of rock? And the answer might be no, okay? And we have to come to that realization. One of the things that drives geologists in a lot of cases is wanting to know what the rocks were originally, what the composition originally was. And I think that we have a tendency to presume that the geophysical response always comes from the subcrop, the rocks that we're seeing. And again, we have to be able to let that notion go in some cases and go with different models if the data don't support it. So I'm going to talk about the data I typically use to do regional mapping, and that's typically things like TMI and Bouguer gravity, and that's really the primary data that you're going to use. So maybe you've got a rock type that's got a certain range of magnetic susceptibilities, let's say, and then the concept would be that you would try to trace those values elsewhere, and potentially those rocks are the same. Now there are a lot of filters that our speakers later in the day will be talking about, things like the first vertical derivative, for example. Those have specific uses, and a lot of them are finding edges, and I'll show you some images of that, but they're not necessarily for mapping out different types of rock units, okay? They're for different things, and we have to use those correctly. And finally, there are ways for us to look into the third dimension, inversions. Omid will be talking about that, and others, I'm sure. Things like multi-scale edges with upward continued data to help us resolve the data in the third dimension, so we can get some idea of how deep a feature is. So I've got a bunch of different images up here from the Clearwater high area here, so that's the geophysical feature. You can see it shows up in the gravity as well, so it's an interesting feature. And I've got a bunch of different presentations of the data, and you'll note that I have two different versions of the TMI up there. And the reason I've done this is that they've been colored differently. And so in this side here, there's a logarithmic color ramp, and that tends to accentuate the highs, the biggest highs, and the deepest lows, which are in blue. The highs are in red on this, or pink. And what that does is it actually drowns out some of the detail. So if you put it on a linear ramp, you're going to see more detail. And you'll see that the Clearwater magnetic high isn't really that profound a high at all. Regionally, there are much more stronger highs in this case. So coloring things differently, adding relief to the image, which is done over here, can help you to interpret where the features are a little bit better. And then there are a number of filters I showed here. The first vertical derivative is an edge finding tool, and the guy who made all these images is a geophysicist from the Geological Survey of South Australia, and he really swears by black and white images for edge picking. He finds that he thinks the colors basically seduce you into seeing things that might not be there. And so he likes to use black and white. And one of my favorite images is automatic gain control. And what I like about it, on this image, you're weighting all the highs the same and all the lows the same. And it's great for structural mapping. You can find edges like shear zones, but what's neat about it is in this area here, you can see there's a region of like structural pattern, even though there are very different magnetic responses in that same region. Okay, so it allows you to interpret structure really nicely. The gravity is telling us something. What I've turned on here are the worms what Phil did with these is he upward continued the data, which basically simulates that the collector was higher above the ground surface, and he's done that for a number of different heights. And it allows you to see the deeper features in the data, and that's what I've got turned on here. And you can see that this Clearwater feature is a pretty deep-seated thing, and it's full of granites, but it's not the granites necessarily that are giving us the response here in the gravity. There's some sort of a crustal scale feature here that's controlling where those granites were placed. Okay, so case studies. Protolith mapping, I'm going to talk a bit about that first, and then I'm going to continue that in a geology compilation discussion. And then finally I'm going to talk about patterns you can see that might be related to alteration. So let's talk about protolith mapping. This is what, so geologists are, I find we're a little bit desperate at times, and when we run out of outcrop or don't have drill cores, we assume that we can use another data source to figure out what the stuff is that we can't see. And so, there's a lot of hope that's used by us. I use commonly aeromagnetic data to try to interpret geology. And there are a lot of factors I think you need to consider when you're doing that. So the Athabasca Basin area is dominated by high-grade metamorphic rocks. Okay, so rocks that have been cooked and modified. Or one of my old professors used to say they've been violated. So we're assuming, though, that there was magnetite in the protolith when we're protolith mapping. I think is what we are actually thinking. And that's a big oversimplification, because we know that magnetite grows during prograde metamorphism, particularly at high grades. Some of the melting reactions lead to accessory magnetite. So if you had, say, a granodiorite at Flin Flon, which is green schist facies, and a granodiorite off to the northwest that's high grade, it's the same rock protolith, but the magnetic responses can be quite different, actually. Magnetite also forms on the retrograde path, particularly in high-grade rocks, things like pyroxene. When they react out, you see in thin section, orthopyroxene is often replaced by a little patch of biotite. So when it gets hydrated, there'll be a little opaque speck in the middle of that, and that'll be magnetite. So it's growing on the retrograde path. There wasn't enough iron taken up by the biotite to use it all. But if you continue to hydrate those rocks, you tend to react all the magnetite out. And so that complicates things when you're trying to map. So two rocks, depending on how hydrated they are, might have a different magnetic response. And this is particularly the case in high strain corridors of fault zones, where lots of fluids have passed through. So we're looking at an area in the north-central Athabasca Basin, right on the rim. Up here, Stony Rapids is right here for reference, and I've got on the total magnetic intensity here, and I've got the compiled geology laying on top of the total magnetic intensity on the right. And so when most people look at this map, they say, well, that anomaly and those two anomalies are very similar, actually, in their values. Those have to be the same thing. But when you look at the map, they aren't. And I can confirm that they're not. Well, what about these two things here? You go to the map, no dice. No, they're different rock types. And that makes interpreting this anomaly here really challenging. You don't necessarily know what it is unless you've drilled it. Okay, well, what about this area here? This looks like a domain of similar response, but there are different rock types in there. And I guess my point here is that this isn't so easy, all right? So this area we know it's a low, it's got supercrust metasedimentary rocks. But over here is a similar low, and there aren't any supercrustal rocks there. It's a different pattern. So the pessimist in me says that really the only thing I know what it is on this geophysical image is these dikes here. These are mafic dikes. And Sean here, and Sean Bosman, not Sean Harvey. I don't discuss stuff with Sean Harvey. But Sean and I were discussing these mafic dikes, and we make the presumption that these dikes, based on their orientation, are part of the Mackenzie swarm. But we've actually never dated these dikes in the Athabasca Basin. We've got one age for the Mackenzie dikes in Saskatchewan. It comes from a Pluton and the Wathman batholith, and it actually doesn't have this orientation. So we don't even know. There are 3 suites of mafic dikes in the Athabasca Basin. I'm not sure we even know which one this is. Okay, so protolith mapping is not so easy. So now I'm going to go to the Key Lake area, and I'm going to use compiled geology again. It's the same geology data set, the 250 scale compilation geology. And I'm going to compare it to the aeromagnetic signature here. And so I've just used the term compilation a bunch of times in here. And so what's a compilation map? Well, it's an interpretation. Okay, it's not the source data. Somebody's taken the source geological data and interpreted it and made polygons out of that. And so when you look at this one, it looks like, you know, maybe these pink units are highs there. The pink unit's high. There's a bit of a high here. Maybe the brown units are lows. And so maybe you could interpret this geology to the northeast using this compilation map. If you look at the source geology over here, what you find is there's a lot of gray stuff on this map, and that's cover. Okay, so there's not a great deal of exposure here. There's a little string of outcrops right through here that help to interpret this area here. I think about 8. And then there's this whopping big polygon that's held down here by boulders, actually, on this map here. There's no outcrop there. And so you start asking yourself, well, how did they draw the polygon? How did they come up with this? And the answer is that it's an aeromag interpretation. Okay, so they didn't have a lot of data. So the compilation map is an aeromag interpretation. So now, if we go to interpret this area here with this map, we're using an aeromag interpretation to make an aeromag interpretation, not the source geology. Okay, so you have to go back to the source data to help you with understanding the confidence of what you're doing with mapping. And this is a great example of an area where you need to do that. Okay, so what about alteration? Now I'm gonna suggest that in the Athabasca Basin area, which has been highly reworked in the late part of the Paleoproterozoic, that we're going to see lots of responses that have to do with alteration here. And when we flew one of our new surveys, you can see the edge of it is right here. You can see the difference in the data quality here. This feature here caught my eye, this low here, and I was talking about this area here. We know there are metasedimentary rocks, and you might be think that this could be these lows could be metasedimentary rocks. And what was most interesting about it, though, was this flat signature that corresponds to this area. Whereas this area here, this is on the automatic gain control, the image I like. This area here with the metasedimentary rocks has a pretty different structural pattern. And there's a similar pattern here, and this pattern is actually tied to linears. So what I did when I saw this pattern here is I went back to a compilation map, actually, and tried to figure out what might be the geological reason for that. And sorry, it's a black and white map, but the most important thing here is this cross-hatched area on Chris Gilboy's 1980 compilation for the area. And that cross-hatched area has to do with the distribution of something they called late muscovite granites. And so I guess those granites, these late intrusions, could have been responsible for the response. Now luckily we had a bedrock mapping project going on at the same time. So I pulled out those maps, and actually the late muscovite granites are these little things here, okay, and little dikes. So certainly I don't think, at the subcrop at least, those things are responsible for that magnetic signature. But a late intrusive event like that pushes fluids around with it too. And there's a strong chance that this feature has to do with alteration related to the emplacement of these granites. And again, that's an interpretation, but I think it's a fairly reasonable one in this case. Okay, so let's start integrating a bunch of data sets here. So now I'm showing you TMI topography here and Bouguer gravity for the southern part of Saskatchewan. So just for reference, La Ronge is up here, Lac La Ronge there, Saskatoon and Regina, and it turns out we're all in the same geophysical feature, all these communities. I don't know how that worked out, but it seems to be true. So we've got this big or it's not a big maglo, it's a big maglo in places. On the edge of what's known as the Sask Craton here, there's another one actually on the other side of it. And you can see there's a feature in the gravity that mimics that feature. And I'm always amazed that ice flow is partly controlled by, appears to have partly been controlled by features that are in the basement below over a kilometer of Phanerozoic sedimentary rocks in the Williston Basin. I find that pretty interesting, that we have such similar topography patterns to the geophysics, which is way below. So there must be a reason for that. So one other thing that corresponds with this geophysical feature is something called the North American Central Plains Conductive Anomaly. I've drawn the edges of it here, and it follows right along the edge of this anomaly. And actually, here's the 49th parallel right here. So this thing is 2,500 kilometers long. And somebody's gone out north of La Ronge and gone to an outcrop and said, well, you know, I saw some sulfides in an outcrop there. And those are metasedimentary rocks. I bet you that must be the reason that there's a conductive anomaly there. And when you look at a cross section, okay, again, here's the base of our crust right here. So we've got a seismic section, we've got conductivity, or resistivity in this case. So these are the conductive areas. Draped on top of that seismic. And you can see there's a conductive anomaly that actually goes across major geological boundaries here and extends down really to the moho. And so later paper by this author that explains that there's a conductive anomaly in the mantle underneath this thing as well. So what are the odds that some supercrustal rocks north of La Ronge are responsible for this crustal scale anomaly? And I would say they're basically zero. Okay, there's some sort of a structural feature that's cutting across boundaries here. It's probably pretty late. And so this is potentially some sort of an alteration system related to faulting. It could be graphite at depth. Somebody's speculated in these fault zones. So we can't always explain the anomalies, the stuff that's right where we can see it, okay, as I think is the messaging here. And so that's how I'm going to end up here. So first bullet said just that. You might not be able to explain your anomaly with the observed geology. You might have to drop some of your model, your genetic model, and come up with a new model. That's how we learn stuff, and that's how we get better. Okay, so we need to use multiple data sources. I hope I've showed you that with the last slide to help to interpret our geology better. In the Athabasca Basin, I think the genetic origin of these anomalies, and we're going to talk about it, can be pretty complicated. There's a lot of alteration here, and that's what I think we're going to learn a lot about today. And, you know, you might have to go back to your manager and say, you know, I can't map the prolith. I can't do it. I don't have enough information. And you know, quite frankly, we're looking for epigenetic mineral deposits here. I don't know why we want to map the prolith, quite honestly. It should be overprinted by the mineral system. And again, the last bullet here is how I started. We got to be able to work together to get the best models. It's what we have to be able to do. Okay, so it's not voodoo. You just don't understand it. Okay. Thanks. You're supposed to use the microphone.
Are there any questions?
I'll start the ball and run quick.
Okay.
This is actually just more of a geological question. Those late muscovite granites, is there an age in those?
Yeah, she did date them, and I think it's 1803. Yeah. So exactly what you'd probably expect for an age. And that's not an uncommon age, actually, in fault zones in the Athabasca Basin for late pegmatites and things like that. So these things are popping up along structures, and that's a pretty common theme. So some of the first fluids on these structures were actually magmas.
One of the things that, I'm not sure Alan Jones's description, but those deep-seated conductive features I occasionally heard are not so much related to a mineral like graphite, but they may be more water content.
Could be, yeah. Could be something like that.
Which implies a porosity and a permeability that doesn't exist elsewhere.
That's right.
Because there's a lot more water than there probably is graphite.
That's right. Yeah, and this is an important point because, you know, at the end of a big orogenic event, so most metamorphic reactions generate water. We talk about the rocks being dehydrated. Well, at the end of these events, you start to exhume rocks, and so the water basically, the lithostatic pressure is relieved from that fluid, and it tries to find ways to get up and boil, basically. And there are corridors like this, probably in the basin, and this is one of them for sure, where the orogenic event dewatered. That's what these things probably are.
Kathy? the automatic gain control, can you explain what's going on with that?
Okay, well,
Sorry, I know.
so I'll try to do this right. And then Omid's going to be talking about it, but just do it. Basically, the idea is you weight, so you don't have a range of sort of highs and lows. You weight the anomalies the same. Okay, so all the lows are the same weight, all the highs are the same weight. And it makes it really a structural map. They were nodding. Okay.
Thank you,
thanks.
Colin.